In this video, we're going to analyze a three-phase induction motor and calculate its full load speed in RPM, full load current in amps, and full load torque in pound-feet. Let's start by looking at the motor specifications. Let's tackle our first question. What is the full load speed in RPM of this motor? To find this, we first need to calculate the synchronous speed of the motor. For an induction motor, the synchronous speed depends on the frequency and the number of poles. The formula for synchronous speed is 120 times the frequency divided by the number of poles. In our case, we have a 4-pole motor operating at 60 Hz. Plugging these values into our formula, we get 120 times 60 divided by 4, which equals 1800 RPM. This is the synchronous speed of our motor. Now, an induction motor doesn't run at the synchronous speed. The difference between the synchronous speed and the actual speed is called the slip. Slip is usually expressed as a percentage and is defined as the difference between the synchronous speed and the actual speed, divided by the synchronous speed. From this definition, we can derive a formula for the actual speed. N equals N sub S times 1 minus S, where N is the actual speed, N sub S is the synchronous speed, and S is the slip. Given that our motor has a 10% slip at full load, we can calculate the actual speed as 1800 RPM times 1 minus 0.10, which equals 1,800 times 0.90, giving us 1620 RPM. Let's visualize what's happening with the motor speeds. The stator magnetic field rotates at the synchronous speed of 1800 RPM. However, the rotor always rotates a bit slower than this magnetic field. In our case, the rotor turns at 1620 RPM, which is 10% slower than the synchronous speed. So, the full load speed of our motor is 1620 RPM. Now, let's move on to our second question. If the full load voltage is 230 volts, what is the full load current in amps? To find the current, we need to use the relationship between power, voltage, and current in a three-phase system. First, let's calculate the output and input power. The output power is given as 10 horsepower. To convert this to watts, we multiply by 746 watts per horsepower, giving us 7,460 watts. The input power can be calculated by dividing the output power by the efficiency. With an efficiency of 90%, the input power is 7,460 divided by 0.90, which equals approximately 8,288.9 watts. For a balanced three-phase system, the relationship between input power, line voltage, line current, and power factor is given by this formula. Input power equals square root of 3 times line voltage times line current times power factor. Rearranging to solve for current, we get current equals input power divided by square root of 3 times line voltage times power factor. Plugging in our values, we have 8,288.9 watts divided by 1.732 times 230 volts times 0.80, which gives us approximately 26.0 amps. Let's visualize what a three-phase system looks like. In a three-phase system, we have 3 sinusoidal voltages that are offset from each other by 120 degrees. In a balanced system like ours, each phase carries equal current, but they're out of phase with each other. So, the full load current of our motor is 26.0 amps. Finally, let's calculate the full load torque in pound-feet. We can approach this in 2 different ways. Let's explore both methods. For method A, we'll use the relationship between power, angular velocity, and torque. First, we need to convert our speed from RPM to radians per second. The formula is omega equals 2 pi times n divided by 60. Plugging in our full load speed of 1620 RPM, we get 2 pi times 1620 divided by 60, which is approximately 169.65 radians per second. Now, the relationship between power, torque, and angular velocity is power equals torque times angular velocity. Rearranging, torque equals power divided by angular velocity. Plugging in our values, we have 7,460 watts divided by 169.65 radians per second, which gives us approximately 44.0 newton meters. To convert from newton meters to pound feet, we multiply by 0.73756, giving us 44.0 times 0.73756, which equals approximately 32.5 pound-feet. Let's also check our answer using method B, which uses a convenient formula that directly gives torque in pound-feet for motors rated in horsepower. The formula is torque equals 5,252 times horsepower divided by RPM. Plugging in our values, we have 5,252 times 10 divided by 1620, which gives us approximately 32.4 pound-feet. As we can see, both methods give us very similar results, which confirms our calculation. Let's visualize what torque means physically. Torque is a measure of the rotational force that the motor can provide. In our case, the motor produces a rotational force of approximately 32.4 pound-feet at full load. So, the full load torque of our motor is 32.4 pound-feet. Let's summarize our findings for this 10 horsepower, 3-phase, 60 Hz, 4-pole induction motor. The full load speed is 1620 RPM. The full load current at 230 volts is 26.0 amps. And the full load torque is 32.4 pound-feet. These calculations are essential for properly sizing and applying induction motors in various applications. Thank you for watching.